Hey, space fans! Today, we're diving into one of the wildest events in the universe, supernova explosions. What really happens when a star dies? Let's break it down, Type 1a versus Type 2, and explore why these cosmic blasts actually matter to us. Picture a star, dozens of times bigger than our sun. It sputters out its last breath, and then, boom! In seconds, it releases more energy than our sun will in its entire lifetime. Here's the twist. Not all supernovae are the same. Type 1a and Type 2 might look alike at first, but the way they explode is completely different. By the end, you'll never confuse them again. Let's start with Type 2, the classic core collapse supernova. These come from massive stars, at least 8 times heavier than the sun. They burn through fuel, hydrogen, helium, carbon, all the way up to iron. Iron is the deal breaker. Fusing it actually drains energy instead of creating it. Once iron takes over, the balancing act ends. Gravity takes control. The core collapses in a blink, crushing matter into a neutron star, or if the star is huge enough, a black hole. Then the outer layers rebound off that dense core and explode outward. That's a Type 2 supernova. For a brief moment, it can outshine an entire galaxy. And here's something mind-blowing. The blast spreads elements everywhere: oxygen, silicon, calcium, even the iron in your blood. Yes, you are made from the guts of dead stars. Quick pause. If this is blowing your mind so far, hit subscribe to Space Science Simplified. More cosmic deep dives are coming your way. Now, let's jump to Type 1a, which is a bit stranger. These don't come from massive stars, they come from dead ones. White dwarfs. A white dwarf is tiny, about the size of Earth, but carries the mass of the sun. Usually, it just cools quietly, but put it in a binary system with another star, and things get interesting. The dwarf starts stealing gas from its companion pile by pile until it hits a critical tipping point, around 1.4 times the sun's mass. And then, fusion goes rogue. The entire star explodes in an instant. Unlike Type 2, there's no leftover core. The white dwarf is completely gone. Astronomers love Type 1a supernovae because they explode with nearly the same brightness every time. That consistency makes them perfect standard candles for measuring cosmic distances. And using them revealed something shocking. The universe isn't just expanding, it's accelerating. That's dark energy at work. This leads to the big question. How can we tell them apart? At first glance, they might seem similar, but their fingerprints tell the real story. For a Type 1a, you'll find no hydrogen, a smooth fade in brightness, and strong signals of silicon and iron. And for a Type 2, it has loads of hydrogen and a distinct plateau in brightness as that hydrogen recombines. Let's do a quick recap. Type 2 comes from massive stars and collapses into neutron stars or black holes. Type 1a comes from white dwarfs and binary systems, obliterates completely, and serves as our cosmic standard candles. Both are powerful cosmic recyclers, forging and scattering the elements that make new stars, planets, and life itself. Here's a fun fact. Type 2 explosions release 99% of their energy as invisible neutrinos. Only about 1% shows up as light and debris. With Type 1a, most of the energy is in that brilliant light and motion. Ultimately, why should we care? Because without supernovae, there's no Earth, no life, no you. Every single atom in your body has a cosmic origin story that started in a dying star. Next time you look up at the night sky, remember this. Some of those twinkling lights are the afterglow of explosions that made everything you see and everything you are. Thanks for joining this stellar journey. Don't forget to like, subscribe, and share. Drop your questions in the comments. I love hearing what you think about our universe. See you next time.